Hello, friends, and welcome to yet another lecture on chemical engineering thermodynamics. I am Professor Arvind Prasad. Today, we will be looking into problems on reaction equilibria. Without wasting much time, let us go to the problem. The water gas shift reaction, carbon monoxide plus steam gives you carbon dioxide plus hydrogen, is performed in a reactor. The equilibrium constant for the reaction is given by the expression K equilibrium is equal to exponential 4577.8 over T, where T is in Kelvin, minus 4.33. Now, the reference for this expression is JMO, Chemical Engineering Progress, Volume 58, 1962, particular 33 edition. Now, here we need to understand is that the expression for K should never be calculated by introducing a very uh, favorite idea that the heat of reaction does not change with temperature a lot, and therefore we can calculate the value of K, which is calculated at 298 Kelvin, and simply use the expression ln K is inversely proportional to temperature and directly proportional to the heat of reaction. Now, since the heat of reaction is constant, we can easily integrate this expression, and we can get an expression that K is inversely proportional to T, and because H is constant, we can do the calculations. Now, here there is an error. The error is that we are assuming two things. Number one assumption is there is no entropy of reaction, which by itself reactions do have entropy of reactions. And second is assuming that the H, that is the delta H, that is the heat of reaction, also is a very weak function of temperature. Now, mind you, these assumptions are right, but they are right only for certain kinds of reactions. But for for certain reactions, they are not right, and they would lead not to a very good, accurate value of K. And then what happens also is the tendency that we calculate the value of heat of reaction at 298 and use the expression K is directly proportional to the heat of reaction, which is a constant, and inversely proportional to the temperature, and integrate and use this reaction for any and every temperature. This itself is pretty erroneous because the heat of reaction does change with temperature. Now, for very small changes in temperature, it is fine. But for very large changes in temperature, it is wrong. So, therefore, it is always suggested that you go to the search, do a reference search or do a literature survey and get the value of equilibrium constant, which are published, and then use them to solve any problem. However, one needs to understand, and I would like to make everybody aware, professional engineers as well as students, that K gives you only the equilibrium constant. But remember one thing, for any practical reactor, the equilibrium is never reached. Why? Because what is the time required to reach equilibrium? Well, it's infinite. And there's no infinite time in any reactor. Any reactor has a specific amount of time in which the reaction is going to occur. Now, how quickly will the reaction reach the equilibrium value will depend on the kinetics of the reaction. Now, this is a subject matter of reaction kinetics and is beyond the scope of this topic. Nevertheless, let's calculate the value of epsilon, that is the extent of reaction, if for every mole of carbon dioxide, 1 mole of steam enters the reactor and the temperatures are of operation are 1100 Kelvin, 1200 Kelvin and 1300 Kelvin. I will solve most of the problems using Wx maxima. This is a computer algebra system, and I suggest every professional and every student learn this. It's a free software. You will see the advantages of using a computer algebra system vis-a-vis a conventional programming language like Fortran, Python, C, or whatever to solve your problems. Here, solutions are more direct. The interaction of the program is more human-like. You do not have to learn any programming language. Let's go ahead. Now, I have copied these two slides on Maxima, and there they are. Problems on reaction equilibria by Professor Arvind Prasad. Well, the problem is this. Now, the reaction is unaffected by pressure. Now, this is understood because there is no change in moles in the reaction. There are 2 moles of reactants and there are 2 moles of products. Now, if epsilon is the extent of reaction, then the moles of carbon monoxide, hydrogen, carbon dioxide, carbon monoxide, steam, carbon dioxide, and hydrogen at equilibrium are 1 minus epsilon, 1 minus epsilon, epsilon, and epsilon. Now, it's fairly simple here. The moles at the end of the reaction or at equilibrium is going to be the moles fed plus the stoichiometric coefficient multiplied by the epsilon. Now the stoichiometric coefficient, as you can see, for the reactants is minus 1, and for the products is 1 and 1. Mind you, no carbon dioxide and hydrogen was fed. So we get 1 minus 1 as the moles of carbon monoxide at equilibrium. For steam, it is 1 minus epsilon. For carbon dioxide, it is epsilon, and for hydrogen, it is epsilon. The total moles at equilibrium are 2. We add all this and we get the total number of moles at equilibrium. 1 minus epsilon, 1 minus epsilon makes it 2 minus 2 epsilon, and this is 2 epsilon, so we add it and we get 2. The mole fractions of each component are, that is carbon monoxide is 1 minus epsilon by 2, steam is 1 minus epsilon by 2, carbon dioxide is epsilon by 2, and hydrogen is epsilon by 2. Now, for simplicity's sake, to solve the problem, I can use epsilon and write the expressions, but I would substitute epsilon with x. Now, let's write the expression for the equilibrium. So, for the equilibrium constant or K, the expression is going to be the products the mole fraction of the products divided by the mole fraction of the reactants. So we are going to have here 1 minus x over 2, and the second one is also going to be similarly 1 minus x over 2. Pardon me, this should not have been there because the stoichiometric coefficient is 1 and not 2. And we get the resulting expression. Therefore, we have the resulting expression x square over 1 minus x square. Now the value of K, the equilibrium constant, can be written as, if you have to write it in maxima, K is a function of temperature, and this is equal to the exponential of 4577.2. 8 over the temperature minus 4.33. There we go. So we enter the expression. To enter the expression in maxima, you press shift and press enter. Now here I would like to make a slight change and write this as exp e whole raised to. And we write it here. The term E is percentage E. And there we get our expression. This is EPS E, that is the standard E or E that we have in mathematics, which is 2.303 if you take the log of it. Yeah, now we have the expression for K. Now, the first temperature that we have is 1100 Kelvin. So we can write the expression for solution. So expression 1, that is for case number 1. So for case number 1, we have K 1100 minus the expression for the equilibrium. So it is going to be now this naturally arises because K is equal to this expression. So what I have written here is I have defined another expression which is nothing but K minus this expression, the expression that we have for equilibrium, and we get it. Now we solve this expression to get the answer. Now we solve it. So we write the solution as solution 1. So this is solution 1, and if we need I'll come to that later. So to get the solution, we write exp n 1, that is the expression, and solve it for x, and we enter it. And here we see that we get a analytical expression for it. Now, how do we get a numerical value for the analytical expression? Well, there are two ways for it. The first direct way would be to write float before solve and press enter. And there we have the values of x. So the value of x or the value of epsilon for 1100 degrees Celsius is 0.4789. Now the value for 1200 would be go up, come here and go to cells and go to cells, evaluate cells below. Now it will recalculate for 1200 and give you the value. It is 0.43. Mind you, it was 0.47 initially. Let's do the demonstration once again. 1100 cells, evaluate cells below, and for 1100 you have 0.4789. That should be 0.48 or 48% conversion. Now for 1200 we solve this and we get 43.5, that is 43.6% conversion. And the third value, that is 1300, we get the value as solve cells below 0.4. So from 48% it came to 43% and it came to 40%. Now this is quite natural. Note that this reaction is exothermic. Therefore, as we keep increasing the temperature, we get the correct conclusions from our calculations that the equilibrium now is shifting towards the reactants. When it is shifting towards the reactants, it's an obvious fact that the conversion is less. So that is the end of my presentation. Hope you have learned two skills today. One, one is chemical engineering, thermodynamics, and the second one is a motivation to learn computer algebra system WX maxima. Have a great day. Fine, guys, that was the end of the lecture. Please like and subscribe my videos. They motivated me a lot. There are some comments which are coming from students to make lectures on topics which are unrelated to chemical thermodynamics. Please send me requests only to make lectures on chemical engineering thermodynamics, not on any other branch of chemical engineering, because the total focus of this playlist and this channel for now is going to be to unravel chemical engineering thermodynamics for professionals and students. And that's what is the chief motivation. I remember when I was studying, it used to be a subject which nobody understood. Until today, the opinion remains the same. Many people who leave the course of chemical engineering at bachelor's and even at master's say that this subject has no practical application. Well, the idea is why it does not have any practical application. No, it's not that way. It's just that we have not understood it enough to apply it to our practicing careers. If we had understood it well, we would have applied it every day or every chance which we got it. But somehow it's a subject which is not taught properly, not understood properly, and therefore people just fail to appreciate it. So these lecture series are something which is trying to correct that opinion of thermodynamics. I hope my viewers will help me in this project. As of now, have a great day. Goodbye.